Howdy, my name is Jason Jordan and I'm a senior meteorologist at the National Weather Service in Lubbock, and today I'm going to show you how we use the West Texas Lightning Mapping Array in operations here at the Weather Service in Lubbock. Before I go forward, I got to thank our Science and Operations Officer Steve Cobb, and then also the professor that is heading up the lightning research at Texas Tech, Dr. Eric Bruning. Without those two support, none of this would be possible. So what are we going to cover today? The first thing we're going to go through is a description of how we get the LMA data in our office. The cases that we'll be going through after that, 1, 2, and 3, we're going to be looking at convective evolution, case of Thundersnow, and then how we use the LMA for decision support. Also look at some future collaborative research, some cool things that we're doing, and then some conclusions. So how exactly do we get the LMA data? Well, Texas Tech has deployed the sensor network across the central part of our county warning area, and that's about 11 to 12 sites that collect the data, send the information via cell phone modem back to Texas Tech. It goes into their network. They use the computer to locate all the sources, and then there's two ways from there that the data starts to get shipped out. The first way that we've been using it for the last 3 years is that it goes through a WebSocket server, and that sends data through the NOAA firewall and into our office to a single Linux box that's running a program called SOCAT. This allows those packets to be rebroadcast out on our internal network so that any Windows PC or Linux box in our office outside of the AWIPS network but inside the NOAA firewall can access that data and display it. So therefore, if we have 12 PCs that are running the LiveLMA software, all 12 of those will be able to connect to the data, but it's only coming in through one source. That way, the bandwidth is reduced on the amount that we're pulling in that data. The second way that we're getting data now is that all those products are aggregated for use on the web, and then for AWIPS-II, it gets shipped out via LDM to NSSL. NSSL processes those data into a GRIB2 format that again goes through the NOAA firewall through LDM to our AWIPS-II system, and now we have the ability to ingest that GRIB2 data on our AWIPS-II and display it there. So how exactly does it work? Well, you see the lightning flash there, and about 1 or 2 seconds later, you see the sources show up on the right. This will loop again so you can see that. We've been finding that on the LiveLMA display that the latency, again, is about 1 to 2 seconds, and that's been fairly consistent over the last 2 to 3 years. So why are we using LiveLMA and not something else? Well, at the time when the LMA was deployed across West Texas, we didn't have our AWIPS-II system installed. All we had was AWIPS-I, and the decision was made to wait to be able to get gridded data like this into AWIPS-II, so we could still generate products, but mainly in a research offline and post-event method. So the only real way that we could get data into our office was using the LiveLMA software. So let's go ahead and take a look at some of the convective evolution that we saw, and this is the case. The LMA data can give us an indication early on where the storms that are developing and going through their life cycle are. We can see initiation with some of the first sources before anything on the ground is detected. We can see different things in the mature stage, and then also some things that we're seeing in dissipating stages. Now, when I get into this, I'll explain how we look at what are called sources, but as opposed to displaying the individual points, we can also display a log density plot, and this is a different way of displaying the same data, but allows us to show regions that we really need to concentrate on a little bit more. So our first example here, we have 2 supercells in a tropical environment, pretty rare situation here in West Texas. And you can see that the northern cell is starting to be absorbed by the southern storm. That southern storm then becomes the dominant storm, and we see some characteristic signatures in the LMA data as the storm moves off to the east of the radar. I'll show this loop once again so you can sort of see the convective evolution. The northern cell starts to get pulled in and dissipates as it gets absorbed by the southern cell. Again, this supercell was anchored on an old outflow boundary from a previous storm, and then it cycles again, and then we see continued development again on the southeastern flank. So 2010 to 2020 UTC. This is what the LiveLMA data looks like when we're looking at the sources. I won't get into too much detail about what sources are. I encourage you to do some looking online and trying to understand the terminology that we use, but basically we are using the LMA to detect every point along the lightning channel's path. Up here at the top is basically a time series of all the sources in the window, so the blue colors are the oldest data going to the red colors, which are the newest data. This is an east-west composite cross-section looking from the surface all the way up to 20 kilometers. So this is all the sources in this window below, which is your plan view, again showing all the sources color-coded by time. And then your north-south composite cross-section, again also showing sources colored by time. This window here shows the where most of the sources are being concentrated. So for instance, in this time window, anything that is being detected here shows that most of the sources are coming right around 10 kilometers with a distribution in altitude with those. Two things to note: here's the northern cell. You can see that there's a pretty distinct area of sources taking place here, and here's the southern cell that also is starting to show its own area of sources as it starts to develop. Jumping forward the next 10 minutes, 2020 to 2030 UTC, we notice two things compared to the previous frame. The first thing is that there's just a rapid increase in the number of sources with time. You see a lot of them here in red. And then correspondingly here on the northern storm, they're starting to decrease quite a bit. We're not seeing as many sources. They're getting a little more stretched out in time and in space. As we jump forward another 10 minutes, 2030 to 2040 UTC, two things to notice is that the first one is that pretty much all the sources from the northern storm have disappeared. These were at the very beginning of the time frame. We see some maybe about 5 to 7 minutes inside this time window, but by far the majority of the sources are with the southern storm now. And you also notice there's a pretty good cluster here, which corresponds to where the main updraft location was located. Again, going forward 2040 to 2050 UTC, thing to notice here is that you can see that we're seeing again a concentration of sources in the core of the storm, but we're also starting to see sort of sources going out in two directions. The first one here off to the northeast, and the second one here off to the southeast. Again, this is as the storm is starting to reach its maturity stage, and if you think about supercells on radar, you kind of get the flying eagle look. Well, that kind of corresponds to this as well. Now, as we jump to 2050 to 21 UTC, the next 10-minute window, you notice that the concentration of sources at the core of the storm have pretty well lost. It's kind of spread out here a little bit more to the north and east. There's a lot of sources going out towards the Anvil region, but you also notice that there's now a minima here off pretty close to where the updraft was. And this happens to correspond to where the center of the mesocyclone was with this storm. I don't have the velocity data to show you, but there have been several cases in literature where sources in a supercell are starting to sort of form a ring around the concentrated core of the mesocyclone itself. Jumping forward 2100 to 2010 UTC, I'm pretty kind of sure that it looks like it lost its definition. There still are a lot of sources taking place, but they're very scattered and kind of spread out across a larger region. It's hard to tell if there's a concentrated area in here or in here. But then if we jump forward again, 2010 to 2120 UTC, we can see that the sources have again reconcentrated in this location, indicating another strong updraft. And again, going back and forth, you can see how that change takes place. Now, I'd mentioned earlier that one of the things that we're looking at is the log density plots. And again, this is just a different way of displaying the same data, but as opposed to looking at the individual sources, we're now looking at the actual density. How many sources are taking place on a logarithmic scale inside the core of the storm? So again, you can see the northern storm still has some sources, but you notice that the colors are more of your yellows versus the reds, indicating that there's really not many concentrated sources with this storm, but by far the southwestern storm does have more. As it moves forward with time, you see that the sources continue to be concentrated. And then again here, as we move through, you can see this period where there's the ring inside of the storm where the mesocyclone is the strongest and the sources are concentrated around the outside of the mesocyclone itself. Again, I mentioned that there were other cases. I know one in particular was looking at a similar detection network over the Dallas-Fort Worth Metroplex of a supercell. They also detected the same features in the maximum when the mesocyclone was at its maximum strength, and that allowed it to see sort of the same signature. So this isn't a unique signature by any means. So I've changed things up here in this window. We're still looking at the log density plot, but now we're looking at almost about an hour and a half window, basically 2030 to 21 UTC. And this is where we're starting to see some utility in long time scales of LMA data. Just looking up here at the time series, if you notice, there's these periods where you can see that there's a sort of positive tilt or positive slope to these density plots up here, here, and here. These happen to correspond with updraft pulses within this window. So as the storm is moving with time, you can see that we have an updraft develop here, it kind of tapers off, here's an updraft pulse with the next part, and then it just with cycles with time as we go through these different stages. This also happens to correspond up here at the very top with a bunch of uncorrelated sources. And this also happens to be right after the updraft peaks out, and there's been some studies at the University of Oklahoma, a master's thesis that was published, where they went in and looked at an LMA over the Oklahoma City area and could see some non-discrete sources not really associated with lightning flashes, but what could potentially be at the top of the overshooting top, another indication that the storms are fairly strong. So looking at this is just another example of that feature with the overshooting tops of a pretty much sort of run-of-the-mill thunderstorm, except this one was about 7 o'clock in the morning. Again, it was not really in a tropical environment, but it was rather moist, and it was early on sort of developing with time, and then here about 11:15 you start to notice that we're getting two areas of sources, a different type of source distribution. Well, the storm was intensifying with time, and then as it reached its peak, we started to see all these non-associated sources with lightning taking place up at the top of the storm. And for those of you that are curious, each one of these little parts right here are probably lightning strikes that are reaching the ground. Unfortunately, because of the way that the LMA works, it's very, very hard to see actual lightning strikes on the ground, which is why we use it to compare to the NLDN. Again, the same thing in the log density plots. You can see that there's pretty much a concentration of sources at 2 layers, here about 10 kilometers, another one about 5 kilometers, and then also the uncorrelated sources, not associated really much with any lightning flashes or ground strikes, but still indicating that the storm had reached its maximum intensity about this time frame and then had started its downward trend as it started to weaken. Second case we'll look at is a case of thundersnow. Yes, we do occasionally get thundersnow in Lubbock, and this just happened to be one of those cases. We had a strong cold front that had pushed through the region. Temperatures were falling below freezing. The models that we looked at, the HER, the GFS, the NAM, the RUC, the RAP, they were all forecasting snow somewhere. But the differences in locations were still about 50 to 100 kilometers in distance, so there was quite a bit of uncertainty about where the heaviest snowfall would be. The environment did have some weak elevated instability, but we also had very strong dynamics approaching with a storm system coming in from the west. And as I mentioned, temperature profiles were falling below freezing aloft and at the surface. So here we are, it's about 5 UTC, so about 11 o'clock Central Standard Time. The area here to the northeast of Lubbock, which is right here, had temperatures well below freezing in the upper 20s, and the freezing line pretty much ran about like this across the area. The front was well to the southeast. We were noticing an increase of returns coming in from the southwest. Most of this was not reaching the ground, but the thing that started to grab our attention was that we were starting to see some areas of enhanced reflectivity to the south and to the southeast of Lubbock. Jumping forward again 10 minutes since we were in clear air mode, you can see that the the convection was starting to develop a little bit more. And sure enough, on the LMA, we had our first flash take place at 5:28 UTC. It was very small, very localized, but it was pretty well associated with this storm right here. So we jump forward another 10 minutes, and sure enough, we're starting to see an increase in sources along that convective area. Here's your first flash that we saw. So with time, we were starting to see an uptick in sources. Again, this is about a 10-minute window. And then about that time on radar, you can see how the reflectivity started to increase, and we had our first 3 detected ground strikes on the NLDN. There was just one problem. We did not have the LiveLMA software running at this time because we were not expecting convective snow. So we saw this on AWIPS and decided, well, we might want to go ahead and check the LMA and see what was going on. And sure enough, there continued to be several sources, again looking at a 10-minute window. Now the other interesting thing I want to point out is that most of the sources were located up here in the northern line, whereas the southern line really didn't have that many sources being detected. That continued with time, again another 10 minutes forward. You can see that the band was starting to shift northward with time, and the sources were starting to increase considerably. And just to give you an idea of how the evolution was, we'll take a look at this loop. So you can see that eventually the band started to weaken as it moved north into a more stable environment, but the southern band really didn't pick up too many sources as it moved north. It was really this band that set up on the northern edge of that line. The second thing to point out is you notice that the area of the sources started to increase. You could see some of these flashes, extending easily 100 to 150 kilometers away from the source region. Now, the reason that this was important was that we were able to take that information that we were seeing on the LiveLMA software and figure out where the heaviest snow was going to develop. And sure enough, that gave us a really good estimate. We were able to update our forecast knowing where the convective snow was taking place, that the northern band would be one of more concern versus the southern band, and it ended up lining up quite nicely just along into the east of that as the convective band moved off into the cooler environment, where we ended up with 6 to 10 inches of snow versus where the lightning sort of cut off, and we only ended up with about 1 to 2.5 inches. Case 3 is looking at decision support and how we use this in our office to help some of our people that we work with. The first one primarily that we use it with is the airport here in Lubbock. It is an international airport, but it also happens to be a FedEx hub. So twice a day we get the big 737s that come in with packages that have to be delivered across all of West Texas. And one thing that the airport really doesn't like is when thunderstorms move close to or over location with lightning, having to shut down ground operations when those lightning strikes are getting close enough to the airport, and then having a plane sit on the tarmac with packages that need to be delivered. And this is one of those days that this happened. So here we are at 0 UTC, so 7 p.m. Central Standard Time. We have a line of thunderstorms moving in from the west towards Lubbock. They had kicked an outflow boundary out, so we knew that the convection would generally be weakening with time. And on the LMA, we were still seeing quite a few sources, but they were pretty spread out and then also not really concentrated anywhere along the line. So sure enough, the airport calls us and says, hey, we can see lightning off to the west. We're going to go ahead and shut down operations. Can you give us an estimate of when this activity is going to stop? So we gave them the best estimate. And here we are about an hour later, and the storms finally did make it over the airport, but then they call us and say, well, we're still hearing thunder, but we're not seeing any lightning, and it's starting to rain. Is it okay for us to get our people back out to get the airport ground operations going? So we had to tell them, well, it's still best to hold off because we're still seeing lightning activity in the storm. We haven't really detected anything hitting the ground. That's why you're still hearing thunder but not seeing any lightning hitting the ground. So we can't guarantee that there won't be a lightning strike, but overall the activity is starting to decrease, so maybe in about 15 minutes you could probably be able to restart ground operations at the airport. So it gives us a little better idea of how we can go in and give the airport a better time estimate and a narrower window of when lightning activity is taking place to be able to help them keep operations going or better plan for operations at the airport. The second thing that the LMA allows us to do with aircraft operations is twofold. The first thing it allows us to do is that it allows us to actually see thunderstorms that are flying through the anvil regions or cirrus clouds. The reason that it does this is if you've ever flown on a plane and looked out the window and seen St. Elmo's fire along the window frames or along the leading edge, the trailing edge of the wings, the LMA is actually sensitive enough to pick that up. So not only does it give us an idea if the LMA is performing well, we can go back in and look at online flight tracking to see if the altitude is correct for those aircraft, and then also the time and location. But it also gives us an idea of how things are being routed around the storms. Now, an interesting point that was brought up is that technically, yes, the LMA is working because it's detecting these sources, but once we get into automated algorithms of trying to figure out what's going on within the storms, would this cause some problems? Well, yes and no. The first thing is that it's very correlated, it's very linear compared to the actual lightning strikes you see. They're kind of distributed away from the storms. So it would be pretty easy to write some QC software to check into these and say, yeah, it's a straight line pretty much, and there's quite a few sources within a certain area, so more than likely these are not real, they're aircraft. But we think looking at the raw data actually will allow us to calibrate how well the LMA is performing and then also be able to tell us if we're able to use it well. Now, some other things that we use it for, these are all the high school outdoor football venues across our county warning area. Now, the best part of the LMA in detection efficiency, or how well it can detect the sources, is pretty well centered around Lubbock, since that's where the network is. Once we get out here into the rolling plains, pretty far away from the network, it's going to be a little bit harder because it's kind of like the radar. As the Earth slopes away, you're going to lose the lowest parts of the storm, and then also you lose the 3D detection and go to more of a two-dimensional detection network. But as we move into athletic seasons, and if there's thunderstorms going on, we oftentimes get a lot of phone calls from athletic administrators or school districts wanting to know if they can have their outdoor activity at these facilities, and we can give them a better idea of what's going on. So what's some future research? There's some new fields that we're going to be looking at. Lightning flash sizes, which is again the research that Dr. Bruning's doing at Texas Tech. And then the thing that we're most excited for is that we'll be able to compare it with the Earth Network's lightning data. And if you've had your AWIPS-II workstation with the latest build, this is something you'll be able to look at, the Earth Network's data. If you're still on AWIPS-I or an older build than 14.3.2, it'll be coming up here in a little bit. We're also, again, going to be looking at some different display tools. We're getting our gridded data now in AWIPS-II. You will be hearing more about the Total Lightning plugin that is being developed. I'm on the team that's working on this, and there's some other plugins that we've been using as well for research that we may be able to take in. So like I said, we've got our AWIPS-II installed, and it's working great, and now we're able to get our LMA data in. So what you're looking at here in the top left is the flash density. And so basically you're taking all those sources, gridding it up into a 1 kilometer by 1 kilometer grid at a 1 minute interval, and we're able to see how the storms are evolving. For instance, you saw here we had some yellows, which indicates there's quite a few flashes and sources. Again, here as we get a new updraft pulse, and then just some radar fields to be able to compare it. So we're going to start looking at that, start building some cases to see how well it works, and we have a few here this spring already that we're looking at. Again, I mentioned the Total Lightning plugin that will be coming in here soon, and what this will allow us to do is combine everything that we're looking at. So here's the Earth Network streamer, looking at Earth Networks, what they have for their Total Lightning product. Our LMA in comparison to the side of that, kind of be able to compare on AWIPS 1-to-1. And I will say that this is one of the disadvantages of using LiveLMA, is that it's on a PC. If we're in a very active weather environment, we oftentimes have to have somebody solely dedicated looking at LiveLMA to relay what's going on with the lightning activity, because it's just not in front of us. So once we get into AWIPS-II, and as we have now, we were able to overlay it with our radar fields and not have to sort of split our attention with the PCs in AWIPS-II. So with the Lightning plugin, with that in mind, we'll be able to incorporate all this Total Lightning information that will be coming in and see how it helps us in operations. Now this is some of the other cool research that we can do. So there you saw that beautiful lightning flash that was triggered off those towers. This is slowed down considerably. You're looking at about 5 seconds worth of data, slowed down to about 15. We had our initial sources, and now that flash is spreading northward with time, and in the camera display you can see the cloud flashes taking place. You see it branch out there, and then here towards the end, about 300 kilometers away from our office, there's a ground strike right there. So this is something more that we're using for a research idea, but one of the things that we've seen is that as storms start to weaken, the area of the flashes starts to increase. This was in a decaying MCS case, and this is probably one of the largest flashes in area that we've seen in distance traveled. If you remember back to the first case in convection, all those sources were concentrated towards the core of the updraft. Well, in this case, since these sources were starting to spread out with this huge lightning flash, it's a pretty good indication that we're transitioning more into the decay stage of the storm, and so we're going to start exploring that for use in operations. So we absolutely love having the LMA data here. It's been most helpful for us, especially seeing the live data in operations. It's been invaluable on several warning cases. We even had a case where our AWIPS-I system went down and we were not able to issue warnings here. We had to go into backup mode, but we were able to still look at the LMA data in real time and call up our backup office and say, hey, we're noticing this in the lightning data. Could you go ahead and issue a severe thunderstorm warning because it's rapidly intensifying? And it worked out. Again, the problems have been few and far between. The data reliability coming from Texas Tech has been outstanding. We did have a case this winter because it was so cold and we had several extended cold snaps that the circuit boards had some of the solder on them break loose and render those stations inoperable. But Texas Tech has done a great job getting back out this spring, getting those network stations back up and running so that we're had it available for the start of our convective season. As we get into the Total Lightning plugin, which will be deployed here sometime in the near future, that should help with the workload because all this data will be able to be displayed in AWIPS-II. But I have a feeling that we'll still use LiveLMA as forecasters are fairly comfortable with it here in our office. And we are a very rare case. A lot of times, a lot of offices that have LMAs in their area do not have access to LiveLMA to view it. They're having to get their data through something else. And again, as we start to use this in our operations, we're hoping to develop additional fields. So one of the ones that we are starting to work on is the Flash Area product to see how well that works. But again, we are able to combine all these different data sources and figure out the coding of how we can do this so that we can hopefully help everyone that's listening to this out in the field be able to use Lightning data in their office. Again, my name is Jason Jordan. If you have any questions, please feel free to contact me at my email address. Ask your SUE about Lightning data if it's coming in across your AWIPS workstation, and then we'll hopefully be able to help you learn how to use it. Thank you for your time, and I hope to hear from you soon.